All right, for this part of the tutorial, we're now looking at the interacting species M file. So we start out with some comments again. Difference equations for populations of interacting species A and B have the form an plus 1 equals k1 times an plus k3 an bn. Bn plus 1 equals k2 bn plus k4 times an times bn, which is similar in form to what we saw for the dynamical systems, but these sort of cross terms here, the a and bn terms, are taking the place of that b, that constant b term that we saw before, where K1 and K2 represent the growth of each species in the absence of the other, and K3 and K4 represent the effects of the interactions between the species, proportional to the product of the populations. So this interacting species is relevant to my own personal research. Before coronavirus, I started researching SIR models, so the models of disease spread, and you can actually model the spread of, in an SIR model, it's the S for susceptible and I for infected, um, where the K3 here, we would have K1 would be birth rate, K3 would be the probability of infection on contact between people, um, and this term would actually be negative because you would have people leaving the S group. Then for the Bn plus 1, you would have basically the rate of removal for the K2. So this would be a negative thing for K2Bn. And you would have, however many people are transitioning out of the susceptible are going into the infected. So K3 and Bn would equal K4, or sorry, would equal negative K4 and Bn. So, continuing along, we have the nature of the interaction is specified by the values of these coefficients. So we have competition is when K1 and K2 are both greater than 1, and they're both negative, or K3 and K4 are both negative. Prey predator is when K1 is greater than 1, K2 is between 0 and 1, and K3 is less than 0, K4 is greater than 0. Then cooperation is when we have K1 greater than 1, K2 greater than 1, and K3 and K4 greater than 0. So it's the sort of case for cooperation. Both will grow without each other, but they do even better if they're both together. Then symbiosis is basically, it's similar to cooperation. This is something that I think I saw a little bit of confusion on the last assignment. Symbiosis is similar to cooperation, except for in symbiosis, both need each other. Uh, Whereas in cooperation, they can function without each other. So these systems typically have two equilibria, 0, 0, and 1 minus k2 over k4, and 1 minus k1 over k3. There is a breakpoint there that there shouldn't be. Then we have our clearing the variables. Again, we have a display to ask for the input values for the coefficients. We gather the K1 through K4. Then we calculate the two equilibria, P and Q. And we display where the equilibria will be. Then we're asked to choose the starting values for the populations and the number of iterations. So overall, similar to the dynamical systems, or dynamical system rather, code we looked at before. Then we have our simple little for loop here, which is directly just what we saw in that general model for interacting species, except for the fact that we are rounding to integers because we can't have a fractional population. Then we plot out the results. So it's not too complicated overall in the code, as long as you know the syntax and what you're trying to calculate. So can now execute that. Type in interacting species. So we want input values for the coefficients. So we want to do a little bit of experimenting here. Specifically, you'll want to try out basically doing each one of these different kinds of interactions. So for competition, we want K1 and K2 to be greater than 1. So let's say 2 and 1.5. And then the interaction coefficients for K3 and K4 should be, I believe that was less than 0. Yeah. So let's say that's -1, -2, and we have equilibria at 0, at 0, 0 and 0.251. So let's choose the starting value for species A at 0.1, for species B at 0.5. Then iterations, let's say 10. Okay, so we can see here that it looks like after basically one iteration, species A immediately dies off, and then species B just grows on its own. So, if we want to make this a little bit less trivial, we can repeat that with slightly different values. So I had K1 was 2, K2 be 1.5, interaction coefficient for A, K3 is -1, then -2 there. And let's say starting value for species A will be 0.26. For species B, let's set that at 0.1. The number of iterations, 10. Okay, for that combination, we have both dying off. I won't bother with going through and typing in each thing individually here, but for the purpose of the lab, you should. It's pretty clear how to run this and how to get everything working. So, I encourage you to go through and experiment, see what the different results look like for trying out different combinations of K1, K2, K3, K4, and try to get competition, a prey-predator cooperation into symbiosis. Just experiment and see what happens.